Hi everybody, in this video we're going to be looking at nuclear fission and nuclear fusion. So this is a bit of a game changer, I suppose, in terms of the amount of energy you can get from a reaction. Much more efficient process than burning coal and oil and all those sort of things. Alright, so that's what we're going to be looking at over here. So the big thing, I suppose, when we look at the atom itself, the nucleus, when you put positive charges together, you bind them together, you have to overcome these strong electrical forces because like charges want to repel, and so over a very short range we have this strong nuclear force. And when obviously you split an atom, that strong nuclear force is the binding energy, basically is released as energy in terms of what we're doing here. So this little diagram here, the strong nuclear force is in blue, and then the coulombic forces, okay, and over a short distance, over a critical distance, then that becomes something which we would say is in fact a critical distance for obviously the atom to start splitting apart. So past this point here, you get a thing called spontaneous decay. Over this side, you don't. So when we start looking at nuclear reactions, say example would be using uranium-232. Neutron comes in, and we have to do a few things to that neutron before it actually will be encapsulated inside the uranium-235 nucleus. Generally what we'll get two smaller nuclei, and then we'll get a couple of neutrons being produced. Right? And that's an example of the reaction there. And you get about 180 mega electron volts of energy for every reaction that occurs. Alright, so on average you get 2.5 neutrons. Now, it doesn't mean these are the only byproducts that you'll get. So you can get other different reactions. And again, it's like most things, it's a random process. So you really don't know what you're going to get, but these things are radioactive, which is part of the issue, that we need to actually store those waste products for thousands of years. So generally what happens in the fission process, you encapsulate the neutron inside the nucleus, and obviously we're finding a balance between the strong repelling electrical forces and the strong nuclear force that acts over here. So basically it becomes elongated and you have this critical deformation, and then what happens is the electrical forces dominate and split the atom apart. Alright, so obviously we can talk about the fission reaction being obviously something which is useful, but we can also talk about its destructive parts as well. And we know, obviously it stopped World War II, is the threat of nuclear bombs. The key preference, I suppose, is looking at the mass of the initial reactants is actually going to be more than the mass of the products that you get. And that mass difference is in fact going to be where all the energy comes from. Now this is showing how this particular diagram up the top over here shows how the uranium will go through a chain reaction. So 1 becomes 2, becomes 4, becomes 8, becomes 16. Very, very quickly you got millions of reactions occurring. Alright, so typical fission reaction is basically when you're producing two heavy nuclei, and it doesn't have to be krypton and barium, it can be other things as well, as we discussed. Obviously there are some conditions that you need to do in order to get a chain reaction, but initially what we're talking about here is one basically neutron will cause another fission to occur. Alright, so that's what we're trying to get to happen, is a sustained controlled reaction rather than an uncontrolled. So if we just let this whole process happen by itself, then 1 becomes 2, becomes 4, becomes 8. Very, very quickly you've got an uncontrolled chain reaction. We want to control that reaction inside a nuclear power station. Alright, so that's really what we want to do. Now, a critical mass is the mass that allows a chain reaction to occur. Alright, so basically once you get this reaction going, it will keep going. Right, that's what a critical mass is. Right, and obviously a subcritical mass is one which the chain reaction dies out. A supercritical mass is one where the chain reaction builds up to an explosion, and that's a nuclear bomb. All right, so looking at that, so an example of a bomb, what you would do is you would use an explosion inside the bomb. You would fire these two half pieces of uranium in together, and that will get a reaction, uncontrolled chain reaction occurring quite quickly. Now, nuclear fission power station, you've got basically you've got your core over here, which has got your fuel rods and your control rods in there. Superheat water. We have a heat exchanger where that turns water into steam. The steam then goes through a turbine, and basically very much like most turbines, if we're heating coal or oil or whatever we're doing there, same process. And then you cool the water and then it goes back into the heat exchanger. This is a sealed system, right? So, and then obviously what we do is we cool the water on the external system there, and then that allows us to send electricity through transformers across the people. So the binding energy we'll talk about over here, the mass energy equivalent to the binding energy. So one way to interpret the mass change on is that a nucleon inside the nucleus has less mass than the rest mass outside the nucleus, and that's the preference of where we get our energy from. How much less depends on which nuclei. The mass difference is related to the binding energy, so that's the strong nuclear force that binds the nucleons together. So over here we're generally looking at this is the fission reaction. When we split two things with a heavy nucleon, so the mass per nucleon, and so that's got less mass per nucleon when they've been split into two smaller nuclei. Alright, we'll sort of want to work our way down this particular diagram here. And so that's a preference of E equals mc squared. E is the energy, m is the mass, c is the speed of light squared. And so then when we're looking at that, the mass of the products is in fact more than, the mass of the reactants is more than the mass of the reactants. The energy loss is converted into, the mass loss is converted into energy. All right, I'm going to do a calculation in a second for that. The other process is called fusion. All right, fusion is what allows us to combine things, and again, the proton has more mass by itself than when it's actually inside the nucleus. So therefore, we have a mass loss. All right, so that's again the same process there. All right, so that's interesting. So here's an example of a fusion reaction. We've got deuterium added together to produce helium and a neutron. So what we do is we work out the mass of these things over here. All right, so the mass of the reactants, if you add those things together, you would get 6.688 by 10 to the minus 27 kilograms, very small mass. Our mass of our products, add the helium and your neutron together, you get that figure. Now if you take those two things away from each other, you'll get a mass defect of 5 by 10 to the minus 29 kilograms. All right. Now if you put that into the equation equals mc squared, the mass defect is 5 by 10 to the minus 29. Speed of light is 3 by 10 to the 8 squared, and then you work that out into joules. All right. So and then what we do is divide that by the charge of an electron, 1.6 by 10 to the minus 19, and then convert that to mega electron volts. So that's 2.8 mega electron volts for every reaction that occurs. An example of a fission reaction, all right, we've got californium, all right, decaying to xenon and whatever Ru is, all right, and you're getting 4 neutrons in this particular one. So your mass of your reactants is going to be 4.1859 by 10 to the minus 25. Mass of your products is going to be 4.1824 by 10 to the minus 25. So you've got a mass defect of 3.504 by 10 to the minus 28. Put that into the equation, and then that gives you about 197.1 mega electron volts. All right, so it's a pretty simple process is to actually use that equation to work out the energy of something. Now, really, really important, I suppose, when we start talking about this is that this is an exothermic reaction. Because you're losing energy, losing mass, you're actually creating energy. If it was the other way around, it'd be an endothermic reaction. For those people who do chemistry, will probably understand this, right? Which means that would get colder, right? Endothermic, you actually have to put heat into it, right, to actually get this working. So controlled nuclear fusion, right? The hard thing about that is we have to simulate what happens on the sun. So it needs to get really, really hot. So how do you control something which is super hot? You're talking about millions of degrees C in a container. It would melt most containers. So what we have to do is we need to make this into a plasma, and we need to confine it in a magnetic bottle. All right, so there are lots of examples of how we're trying to do nuclear fusion. I'm just flicking through a couple of different ones there. But essentially, it's this process here. We get two hydrogens together and to produce helium. And the whole thing is these two hydrogens don't want to get close to each other. So what you have to do is you have to get them moving so fast and use pressure and all that sort of stuff, so they don't really have a choice but to get close enough together to fuse. So the problem is at present we're putting so much energy in to do that, we don't get the same amount of energy out. And obviously when we get to that break-even point, then we will be able to, obviously use this as a process of making fuel. Now, it basically uses seawater, right, the hydrogen seawater. So, and the waste products are generally non-radioactive, which is one of the big benefits of that. All right, so obviously, there's billions of dollars, trillions of dollars being put into looking at this particular form of energy. Right. The question, I suppose, for you and for me is, how long can we wait for this? We're still talking, and I think for my whole life, they've been talking about it's been 20 or 30 years away. They're still talking about it being 20 or 30 years away. I know they have made some advances in this, but, I don't think it's that one sort of magic bullet. It's one of the solutions that we need to be looking at here. All right, so anyway, that's a bit of a snapshot about nuclear fission fusion. You do need to understand the two processes. That's what I'll be expecting you to do, is be able to tell me about nuclear fission and the benefits of nuclear fission and nuclear fusion